Motion with constant speed. I'm illustrating a motion. This is motion with constant speed. Now let me throw out a question. When are delta x and the v vector in the same direction in a motion? Answer: always, because the direction of velocity means the direction the car's headlights are pointing in. See, they're pointing to the right, and the car is going in that direction. What's the direction of delta x? Let's draw it. At the initial time, the car is at this point. This is its displacement after 1 second. In 2 seconds, it's moved this far. In 3, this far. If we multiply velocity by time, we find the displacement vector, and we'll generalize with this formula. Because time is a scalar, these two vectors are always in the same direction. This car has traveled a distance of 1 meter in 2 seconds, but it traveled at a constant speed with no acceleration or deceleration. Let's solve this problem. What do we need? A reference point, that is, an origin. Let's put it here. What is this car's speed? 1 by 2, that is 0.5 meters per second. Now let's graph the displacement against time. That's easy. Let's take this axis and flip it around 90 degrees. There's no more primitive type of motion. Here we go. How many meters did it travel in 1 second? 0.5, and then 0.5 more, and 0.5 more. This man doesn't speed up. He doesn't slow down. He travels the same distance every second, so his speed is constant. What do we call this angle? A slope. What does this slope mean? That is, when you take a step in this direction, how much will you ascend? Say you're climbing a mountain. Wherever the steepest rise is, that's the greatest slope. Where's the steepest slope on this mountain? It's the same everywhere. It's constant. Here's the displacement delta x, and here's delta t. Now let's write the slope. Slope equals delta x divided by delta t. This is the tangent of this angle. It gives us the velocity. Conclusion: the slope in the displacement time graph gives us the velocity. Let's work it out. The velocity is 0.5 meters per second. It's constant. It doesn't accelerate or decelerate, so the velocity graph against time for this man comes out like this. His velocity is 0.5 meters per second. That's constant. It's exceeded 3 seconds. The displacement is 1.5 meters. Does that show on this graph? Yes, it does, as this area. Conclusion: the area in the time displacement graph gives us delta x. Speaking of slopes, let me ask you this. Which of these slopes is positive? All of them. Here's how to understand it. How did I define a slope? I asked how much you'd ascend when you took a step, or how far you'd descend. Now put your pens on this point. You take a step forward, and have you ascended or descended? You've ascended. Here you ascend too, so these are all positive slopes. Whether it's above or below the x-axis is irrelevant. Here you took a step to the right, and you descended, so these are negative slopes. Now take a look here too. Now the slopes aren't constant. Which of these are positive slopes? These, see, because when you took a step to the right, you ascended. So we've learned that these slopes are constant. Now then, which slopes are increasing? Let's do this like a math teacher. Draw a tangent. Draw another one here. This slope is steeper. That means that the slope is increasing. Let's do the same thing to this one. The slope decreases. If you don't like drawing tangents, think of it this way. Look at the boundaries. In other words, take a limit. The slope decreases and decreases and decreases, and finally it becomes 0. Horizontal lines have a slope of 0. This is a really useful thing to know. So if someone shows you this and says, "Tell me what I need to know about this slope," you'll answer, "A curve with a positive slope increases." If he says, "Analyze that one," you'll say, "A curve with a negative slope decreases." And that's that.